Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 3, part of this playlist that I'm calling Continuous Random Variables. And let's jump to today's topic, which is the gamma function. Not the gamma distribution, the gamma function. Now, the gamma function appears often in statistics, and knowledge of its properties are important. Now, the definition of the gamma function is this. For any positive number, alpha, the gamma function of alpha is defined like this. It's the integral from 0 to infinity of x raised to the alpha minus 1 e to the minus x dx. Now let's just go through properties for this gamma function. Let alpha be 1, then gamma of 1, so I should put a 1 there, is equal to 1. Proof. Gamma of 1 is 0 to infinity of x raised to the 1 minus 1 is 0, so that's x is 0 goes away. And we're just left with the integral from 0 to infinity of e to the minus x. And I'm going to let you integrate that, and it does integrate to 1. Let x be greater than 1, then gamma of alpha is equal to x minus 1 times gamma of alpha minus 1. That's a recursive formula. So we're going to use the integration by parts technique to prove this. And we're going to define u equal to x raised to alpha minus 1. dv is e to the minus x dx. Then du is equal to this quantity, and v is equal to this quantity, minus e to the minus x. So gamma of alpha, by definition, is this. And then we plug in our integration by parts results, and we get uv integrated from 0 to infinity minus v du. But this minus and the minus that we'd get out front cancel, and it's left as a positive. Now we plug in infinity, e to the minus x goes to 0 so much faster than x goes to infinity, this goes to 0. And you plug in 0 for x, you get 0. So this term goes away. Now, this term will bring down, but instead of minus 2, we're going to represent it as minus 1 minus 1. And then this is in the form of a gamma function, which is gamma of alpha minus 1. And that's what we wanted to show. Now let's let alpha be a positive integer. Then gamma of alpha is alpha minus 1 factorial. Quick proof is this. Gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1. And then you keep repeating that, and it ends up this product, and we get down to gamma of 1. But remember, the recursive formula was only valid for alpha greater than 1, but we also showed that gamma of 1 was 1. And so this becomes alpha minus 1 factorial, as we wanted to show. Let's let alpha equal 1/2. Then gamma of 1/2 is square root of pi. We're going to make a substitution when we integrate this below. So we're going to let x equal y squared over 2. Then dx is y dy. Gamma of 1/2, and then by definition it is this. We plug in 1/2 for alpha. Now we make our substitutions into this, and we get this expression. Square root of 2 e to the minus y squared over 2 dy. We're going to multiply this by a well-chosen 1. Square root of pi over the square root of pi, and the square root of 2 over the square root of 2. And then we're left with this. And while we haven't covered it yet in this playlist, this is a normal density, standard normal density, or at least half of it, going from 0 to infinity. And this is 1/2. Plug it in, we get pi over 2. Let n be a positive integer. Then n plus 1/2 is equal to n minus 1/2, n minus 3/2, all the way down to 1/2 times square root of pi. Now these first n terms can be represented in what's called following factorial notation. You underline it there, and basically you take this term, multiply it times this minus 1, which is, of course, this term, and then minus 1 again. It's like a factorial, but you don't keep going till you hit 1. You only go in terms. It's called a falling factorial. Now, there's also rising factorial notation, but of course we don't need it here. So let's prove it. So gamma of n plus a half, we've showed that it's n minus a half, gamma of n minus a half, right? So this is minus 1 of it. And then we can keep repeating that, minus 1, and that's what these terms are. And we get down to gamma of 1/2. And since that's less than 1, we can't use that recursive formula. But we did show that gamma of 1/2 was square root of pi. Well, that's what we wanted to show. Now, in our illustration is this, gamma of 4, and this is all in base R, gamma of 4 and 3 factorial, note, are both 6, as they should be. Gamma of 5.4, and using the recursive formula, 4.4 times gamma of 4.4, those should be the same, and they are 44.598885. Now, gamma of 7 over 2, according to the last formula we looked at, should be 5 over 2 times 3 over 2 times 1 over 2 times the square root of pi. And notice that they are the same. Okay, well, the next video will be on the beta function, not beta distribution, beta function. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.